Welcome to this video on pulse modulation systems.
Let's begin with the sampling theorem. It states that a continuous time signal can be represented and recovered from its samples if the sampling frequency is greater than or equal to twice the highest frequency component of the message signal, where fs is greater than or equal to 2 fm. The visuals illustrate the process. An input signal xt is multiplied by an impulse train delta t to produce a sampled signal y of t. The frequency domain representation shows the resulting spectrum. The sampled signal y of t is given by the product of xt and delta t. The trigonometric Fourier series representation of delta t is used to expand the impulse train. By substituting the Fourier series coefficients into the expression for y of t and taking the Fourier transform, we arrive at the frequency spectrum of the sampled signal y omega. The spectrum of the sampled signal is shown for different sampling rates. Oversampling, perfect sampling, and undersampling demonstrate how the frequency components are affected. Aliasing occurs when the sampling frequency is too low, leading to spectral overlap and distortion in the recovered signal, as seen in the undersampled scenario. Next, we will explore the different sampling techniques. The three main sampling techniques are ideal sampling, natural sampling, and flat-top sampling. Each technique produces distinct sampled signals from the original analog signal. Ideal sampling involves multiplying the continuous time signal xt with an impulse train, resulting in instantaneous samples. The equations show the time domain and frequency domain representation of this process. Natural sampling uses a train of finite width pulses to sample the signal, where the amplitude of each pulse follows the amplitude of the analog signal during the pulse duration. The output of the sampler in natural sampling is the product of the signal and a pulse train. We use the exponential Fourier series representation of the pulse train to derive the equation. Taking the Fourier transform of the sampled signal and applying the frequency shifting property, we obtain the expression for y omega, the spectrum of the naturally sampled signal. The frequency domain representation of natural sampling shows the replication of the original signal spectrum, scaled by a factor that includes the sinc function, which characterizes the sampling pulse shape. Flat-top sampling uses pulses that have a constant amplitude, equal to the instantaneous value of the analog signal at the sampling instant. The circuit diagram and waveform illustrate this technique. Flat-top sampling is achieved by convolving the ideally sampled signal, S of t, with a rectangular pulse, H of t, to get the flat-top sampled signal, G of t. The equations describe the flat-top sampling process. The sampled signal S of t is defined by the impulse train. The output G of t is the convolution of S of t and the pulse shape H of t. Using the shifting property of the delta function and the convolution theorem, we derive the frequency spectrum G of f of the flat-top sampled signal. G of f is the product of the spectrum of the ideally sampled signal S of f and the Fourier transform of the rectangular pulse H of f. The aperture effect refers to the amplitude distortion caused by the finite duration of the sampling pulses. The rectangular pulse H of t and its corresponding sinc-shaped frequency response H of f are illustrated. The spectrum G of f shows how the replicated signal spectrums are attenuated at higher frequencies by the sinc envelope H of f. This attenuation is the aperture effect. The aperture effect results in high-frequency attenuation in the message spectrum. To minimize this, the pulse width tau should be very small. An equalizer circuit can also be used for compensation. Aperture effect compensation involves using an equalizer, H of f EQ, at the receiver. This equalizer compensates for the frequency roll-off caused by the rectangular pulse shape. The equalizer's frequency response is the inverse of the sampling pulse's spectrum, H of f. The overall frequency response is then a flat characteristic, correcting the distortion. The block diagram shows the flat-top sampled signal G of f passing through the equalizer H of f EQ and a low-pass filter to recover the original signal X of f. Next, we will discuss pulse amplitude modulation, or PAM, demodulation. The PAM demodulator restores the original signal. The PAM signal is fed into a sampling circuit, followed by a reconstruction filter, which is typically a low-pass filter. The block diagram details the demodulation process. The PAM signal is multiplied by an impulse train, and the resulting signal is filtered to recover the message signal. PAM has drawbacks, including a very high bandwidth requirement compared to the maximum frequency. It is also more susceptible to noise effects, and peak powers vary at the transmitter.